in this lesson we are going to learn to use something called the disk method to find volumes of various kinds of solids. Specifically, we will focus primarily on solids of revolution. The next lesson we will also discuss solids which have known cross-sections but are not solids of revolution. Thus far, you probably learned in geometry how to find volumes of some standard solids such as prisms, spheres, and cones. For example, someone probably told you that the volume of a sphere is equal to 4/3 pi r cubed. And the volume of a cone, a right cone, is 1/3 pi r squared h. But no one ever told you why those formulas are true. And furthermore, no one ever told you how you might find the volume of something that's not a standard shape, like a funnel or a pill or a bottle. So today we're going to learn how integration connects the idea of an area under a curve or an area between curves to the volumes of solids. First, we will review how to find the volume of a right prism. So in general, the volume of a right prism, V, is equal to the area of the base times the height. So for this particular cylinder, the area of the base is whatever B1's area is times the height. And here's some specific examples with known bases. The volume for a right circular cylinder is pi r squared h, and you probably know pi r squared is the area of a circle, so the area of the base times the height. And for a box, the area of the base of this box is length times width. Its height is h, so its volume is length, width, height. So next, consider this funky shaped solid we have a picture of here. Suppose we want to find the area of this object. Obviously, there's probably no formula for this, at least not one that you know of. So the best approach is to estimate it using something that you know. So let's start by slicing this up into lots of little pieces. So take the interval from a to v and divide it into lots of pieces. So we'll divide it into n pieces. Each piece will have width delta x equals b minus a over n. Now, each individual piece, as long as they're small enough, is going to be approximately some kind of cylinder. So you pick a sample point somewhere within your little subintervals, so somewhere within there, and you just assume that that little piece is a cylinder because you know how to find the volume of a right cylinder. So what you do to approximate the volume of this piece is you find the area of the base times the height. So the area of the base will be, we'll say it's a of x sub I star, where x sub I star is a point in the interval x sub I minus 1, x sub I. So that would mean that x sub 1 star is some point between x naught, meaning x0, and x1. x1 is somewhere between x1 and x2. And then the volume of a particular slice, we'll say v sub I, will be about equal to a of x sub I star, that's the area of the base, times the height, which is delta x. So that tells us the approximate volume of a slice. Now, to find the approximate volume of the entire loaf of bread, that volume will be about equal to a sum from I equals 1 to n of a x sub I star delta x. So what this is saying is you add up the first slice, second slice, third slice, fourth slice, add up all those individual volumes, and you'll have an approximation or an estimate of the volume of that weird shaped loaf of bread. Now, to get more accurate estimates, you do more slices. To get the exact actual volume, what you do is you take the limit as the number of slices increases to infinity. So the exact volume will equal the limit as n goes to infinity of that expression above, And if you remember your Calculus 1, this, by definition, is an integral. And it's the integral from a to b, a of x dx. So a is where your slices begin, b is where your slices end, and a of x is the area of a cross-section, a general cross-section. So next we'll talk specifically about solids of revolution, what those are, and how we apply this idea to those specific solids. For solids of revolution, suppose we have a curve y equals f of x, and but we care about this curve between some a and some b. Now, how you obtain a solid of revolution is you take this area underneath that curve and you rotate it about an axis. We'll rotate this one about the x-axis. So that's going to produce some kind of shape with some curved side, and we're going to talk about how we might find the volume of this particular shape. So start the same way, divide your interval up. So using what we learned last time, we know that the volume of some weird shape will be the integral from a to b, a of x dx, where a of x is the area of a cross-section. So what we need to do is find the general area of a general cross-section. So I'm going to draw in what I would call an approximating rectangle. So suppose I spin that particular little rectangle that I just drew around the x-axis. The shape you're going to get is going to be a cylinder. The height of the cylinder will be something delta x, and its base is going to be area pi r squared. So the volume of a general cylinder will be a equals pi r squared, and in this case your r is actually equal to f of x. F of x is the y value, it's the distance from the x-axis up to your curve. So the area of your cross-section will be pi times f of x squared. So to find the volume obtained when you spin this region around the x-axis is found by the following formula. The volume is equal to the integral from a to b, pi f of x squared dx. And keep in mind that pi is only there because the cross-sections you have are circles. Your area of your cross-section is a circle. Had that cross-section had a different area, like a square, there wouldn't be a pi there. So let's talk about a specific example now. In this example, we are going to find the volume of the solid formed by rotating the region bounded by the graph of f of x equals square root 25 minus x squared between the lines x equals 2 and x equals 4 about the x-axis. So first of all, you have to recognize that the root of 25 minus x squared is the top half of a circle of radius 5. So there we go, circle radius 5. And if you spin this about the x-axis, the entire solid you would get between negative 5 and 5 is going to be a sphere. We specifically care about the part between x equals 2 and x equals 4. So I will take this region and I'm going to spin it about the x-axis. So the volume of a region is equal to the integral from a to b, a of x dx, where a of x is the area of your cross-section. Because I have a solid of revolution, my cross-section is going to be a circle. So the area is pi r squared. And in this case, r is equal to the root of 25 minus x squared. So my area of my cross-section is pi times the root of 25 minus x squared, that quantity squared. And my slices begin at 2 and they end at 4, so that my limits on my integral are 2 to 4. So this volume is found by finding the integral from 2 to 4 pi times just 25 minus x squared dx. Not so hard. So we'll have pi times 25x minus x cubed over 3, 2 to 4. So we'll have pi times 100 minus 64 thirds minus 50 minus 8 thirds. And as long as you can do basic arithmetic, which is occasionally challenging, we get 94 pi over 3. So the volume generated when you rotate the region underneath root 25 minus x squared between 2 and 4 about the x-axis is 94 pi over 3 cubic units. Next, let's find the volume obtained by rotating the region bounded by y equals 1 minus x squared and y equals 0 about the x-axis. So 1 minus x squared is a parabola reflected over the x-axis and shifted up 1. So looks like this. That parabola intersects the x-axis at x equals -1 and x equals +1. So I slice it up. When I spin about the x-axis, the area of my cross-section is once again going to be pi r squared, and the radius is the distance from my axis of rotation up to my curve. In this case, my radius is 1 minus x squared. So the area of my cross-section is pi times 1 minus x squared squared. So to find my volume, I will integrate from -1 to 1. Function pi times 1 minus x squared squared dx. Now, one thing to notice is this function is even, so you can use symmetry to make your life a little bit easier. So instead of integrating from -1 to 1, we can integrate from 0 to 1 and multiply the result by 2. So that will transform this integral into 2 pi times the integral from 0 to 1. And then next, let's expand 1 minus x squared. When you multiply 1 minus x squared by itself, which we'll do that pretty quickly, you get 1 minus 2x squared plus x to the 4th. Many students often miss this middle term because they think that that power distributes. That is not true. Don't do it. Bad, bad, bad. Okay, moving on. So now we antidifferentiate. The antiderivative of 1 is x. Next we have minus 2/3 x cubed plus 1/5 x to the 5th, evaluated from 0 to 1. So that gives us 2 pi times 1 minus 2/3 plus 1/5. Plugging in 0 yields 0. That's not always true, so be careful. And once you get a common denominator and combine like terms, we end up with 2 pi times 8 over 15, or 16 pi over 15. Suppose we have a curve x equals f of y. So x is a function of y. I'm going to assume it looks something like this. And we want to rotate the region bounded by horizontal lines y equals c and y equals d about the y-axis. So here my slices will be horizontal instead of vertical. The area of the slice is now a function of its y location, so how far up or down it is. And the area, once again, because we're spinning, we have circles, so the area is pi r squared, and the r is equal to f of y. So the area of a slice is pi times f of y squared. To find the volume, we add all the slices up. So begin adding at c, we stop adding at d. So the limits on my integral are now c to d, lowest to highest, pi times f of y squared dy. In this lesson, if you rotate about the x-axis, you will use x's. If you rotate about the y-axis, you're going to use y's. Find the volume obtained by rotating the region bounded by x equals 2 square roots of y, x equals 0, and y equals 9 about the y-axis. Let's start by getting an idea of what this x equals 2 root y looks like. So let's make a table, just plug in some numbers, and it's going to be easier to plug in for y and find x. So if we put 0 in for y, we get 0 out for x. If we put in 1 for y, we get out 2 for x. And if we put in 9 for y, we get 6 for x. So roughly speaking, we have something like this. And we're going to rotate this region about the y-axis. So the area of a slice, once again, will be pi r squared. And in this particular example, my r is equal to the distance from my axis of rotation out to my curve. So that r is equal to 2 square roots of y. So the area of a general slice is pi times 2 root y squared. Simplifying that slightly, that's going to be 4 pi y. Now for the volume, you add all the slices up. So integrate from 0. So y equals 0 is where you start. Y equals 9 is where you end. 0 to 9, 4 pi y dy. Now the antiderivative there will be 2 pi y squared, 0 to 9. And plugging in everything, you have 2 pi times 81 minus 0, or 162 pi. Let's do another example of rotation about the y-axis. In this example, we are going to find the volume of the solid obtained by rotating the region bounded by y equals ln x, y equals 1, and y equals 2 about the y-axis. So first of all, you have to figure out what the graph of y equals ln of x looks like. So you cannot log negative numbers, and you cannot log 0, but the first easy number to log is 1. ln of 1 is equal to 0. All logarithmic functions go through that point. When you plug in, the next easy number to plug in is e. When you have ln of e, that is equal to 1. And e is about 2.7, so we go over about 2.7 and up 1. So roughly speaking, ln x looks like that. And the region we care about is bounded by y, the horizontal line y equals 1, and the other horizontal line y equals 2. So the region we are rotating around the y-axis is this region. So the slices we make are horizontal and not vertical. So the area of my slice is going to be a function of y. So pi times r squared. And you have to know what the radius is. So how far is it from that axis of rotation out to your curve? So to figure that out, you need to take this expression for your curve and solve it for x. So if y is equal to ln of x, we exponentiate both sides and we get e to the y equals x. So my radius is equal to e to the y. Thus the volume is equal to an integral from 1 to 2, because your slices begin at 1 and they end at 2, pi times e to the y squared. And this is tricky, but you have to remember that e to the y squared is really e to the y times e to the y, or e to the 2y. Those powers multiply. So we have pi times the antiderivative from 1 to 2, e to the 2y dy. Now the antiderivative of e to the 2y is e to the 2y. If you just think backwards, if you differentiate e to the 2y, you get e to the 2y times 2. But you don't have times 2, so you need a coefficient of 1/2. So that when you differentiate the pi 1/2 e to the 2y, you get back pi e to the 2y. Evaluate it from 1 to 2. So that will give us pi over 2 times e to the 4th minus e. So my point with this example was that on occasion you are going to have to solve your equation for x. So just be aware that that could happen to you. So in the next example we're going to discuss what will happen if your solid has a hole in it. So here's how that might occur. Suppose you have two curves, call them f of x, we'll call it f of x be a line, and we'll have something like a parabola as g of x. And suppose these curves intersect at x equals a and x equals b. And I'd like to take this region and rotate it around the x-axis. And when that happens, for this particular curve this particular area that I have drawn, you're going to have a shape on the outside that is straight and smooth, and the inside is going to be a little bit curved. Now think about what happens if you take a slice and you look at a cross section. So I'm going to take a slice of the part that is of the spun solid, and I'm going to lay it flat on its side, and it's going to look like this. So I cut a slice and I put it down on the table, and it looks something like this. It has a hole in it. And the way to find the area of that slice is this. So call that R out, and call this R in. The area of the red region, A, will equal pi R out squared, so the area of the entire circle without the middle taken out, minus pi R in squared. And in our particular case, your outer radius, that's the distance from the axis of rotation to the outer curve, that is f of x. And the inner radius is the distance from the axis of rotation to your inner curve, and that is g of x. So my cross-sectional area is pi times f of x, the quantity squared, minus pi times g of x, the quantity squared. And the volume will equal, you sum up all those individual areas, so you integrate from a to b. I'm going to factor out that pi times f of x, the quantity squared, minus g of x, quantity squared, dx. So let's just note also what this formula does not come out to be. It is not f of x minus g of x, the whole thing squared. And the reason not is because when you square that expression, you end up getting f of x squared minus 2 f of x times g of x plus g of x, the quantity squared. So that is wrong. Don't do that. And if you just think about it a little bit, you'll realize why the formula is what it is. All right, let's do an example. So a manufacturer drills a hole through the center of a metal sphere of radius 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? So first of all, a sphere of radius 5 has the equation x squared plus y squared equals 5 squared. If I solve that for y, I get y equals the root of 25 minus x squared. So circle, radius 5, I only need the top half, so there's the top half of that circle. Here's negative 5, here's positive 5. Okay, the hole has a radius of 3 inches, which means that I also have a line at y equals 3. And I get my metal sphere with a hole in it by taking this area and spinning that about the x-axis. Now the first thing you have to determine is what are those intersection points. So when does 3 equal the root of 25 minus x squared? So square both sides and you get 9 equals 25 minus x squared. Negative 16 equals x squared. Equals negative x squared, excuse me. And eventually you'll get x equals plus or minus 4. And now, in order to apply our formula, we need to find the outer radius and the inner radius. So the outer radius, in this case, is root 25 minus x squared, and the inner radius is just 3. So you think you make your general slice. Outer radius is the distance from the axis of rotation up to your curve. Inner radius is the distance from your axis of rotation to the inner curve. So the area of a slice will be pi times r out, which is 25 minus x squared minus pi times 3 squared. Now to find the volume, we need to add up the areas of all our slices. So my volume will be an integral from, now you could find the integral from -4 to 4, but that's the hard way. Because this object has some symmetry about the y-axis, an easier thing to do is to find twice the integral from 0 to 4. Let's take out a pi and simplify. So pi times 25 minus x squared minus 9 dx. So my volume is equal to 2 pi times the integral from 0 to 4, 16 minus x squared dx. Anti-differentiate, and we get 16x minus x cubed over 3, evaluated from 0 to 4. So that will be equal to, when you plug everything in and work everything out, we'll have 2 pi times 64 minus 64 thirds, which works out to be 256 pi divided by 3. Let's do another one of those. So the region R is enclosed by the curves y equals x and y equals x squared, and this is rotated about the x-axis. So let's sketch these curves. So y equals x is this line, and y equals x squared is a parabola. These curves will intersect at the points 0, 0 and 1, 1, and we're going to take the region between the two curves and rotate it around the x-axis. So there is our slice. So the outer radius is the distance from the axis of rotation to the outer curve. For this particular portion of the curves that we care about, the outer curve is actually x. So r out equals x. R in is equal to x squared. The area of my slice is pi times r out squared, so pi times x squared minus pi times x squared squared, which simplifies to pi times the quantity x squared minus x to the 4th. Now to find the volume, you add up all the slices, which is what the integral does. You integrate from, in this case, my slices begin at x equals 0, and they end at x equals 1, so 0 to 1. The areas of my slices are pi times x squared minus x to the 4th dx. So that will be pi times 1/3 x cubed minus 1/5 x to the 5th from 0 to 1, giving us pi times 1/3 minus 1/5. And that simplifies down to 2 pi over 15. The last examples that we are going to discuss in this lesson are solids obtained when you rotate a region about an axis that is not the x or y axis. So for example, if we take the same region that we had in the last example, bounded by y equals x and y equals x squared, and just think if we rotate that about a line, something such as y equals 2. In that case, I will have this object with a hole in it, and the outer edge of the object is going to be curved, and the inner part of it is going to be sort of a smooth, straight surface. Now if I rotate it around something like x equals 2, it's not going to be the same solid anymore. So how you find volumes of the object will change based on what axis you rotate it around. The principle is very similar to what we've done finding the outer radius and the inner radius. It's just there are some details that are useful to walk through some specific examples. So find the volume obtained by rotating the region y equals x and y equals x squared about the line y equals 2. So same region we had in the previous example, y equals x squared, about the line y equals 2. Okay. So now in this case, I make my slice, and I have to find the outer radius and the inner radius. So the outer radius, I'm going to draw that in red, that is the distance from my axis of rotation to my outer curve. So this little distance there, that's x squared. The total distance, that's 2. So your outer radius is actually 2 minus x squared. Now find your inner radius in a very similar fashion. Rn, that's the distance from this axis of rotation to the inner curve. In this case, that is 2 minus x. Okay, so now the area of my little blue cross section, A, will equal pi times r out squared, and r out is 2 minus x squared, that whole thing squared, minus pi times r in squared, so 2 minus x squared. Okay, now to find this, find the volume. So the volume of this solid will be pi times the integral. Now your slices begin at x equals 0 and end at x equals 1, so 0 to 1. If I expand 2 minus x squared, the quantity squared, I get 4 minus 4x squared plus x to the 4th, minus, expanding 2 minus x, the quantity squared, I obtain 4 minus 4x plus x squared dx. Now let's combine some like terms. We have pi times the integral from 0 to 1 of 4x minus 5x squared plus x to the 4th. Now anti-differentiate, and we get pi times 2x squared minus 5 thirds x to the 3rd plus 1/5 x to the 5th, evaluated from 0 to 1. And that will give us pi times 2 minus 5 thirds plus 1/5, which when you get a common denominator and add it all up, you get 8 pi over 15. All right, one more. So that was about a horizontal line, y equals 2. In the next example, we'll take the same region, rotate it about a vertical line. And what you can think is a horizontal line is more similar to the x-axis, whereas a vertical line is going to be more similar to rotating about the y-axis. Okay, find the volume obtained by rotating this region about the line x equals -1. So same region. There's your parabola. Here is your line. And x equals -1 right over there. Okay, so the outer radius is, so that is my general slice. The outer radius is the distance from my axis of rotation out to my curve. Now, much like the example that involved ln of x, I'm going to have to also solve this equation for x. Pretty simple though. That is x equals square root of y. And the other one will be just x equals y. Okay, so the distance, my outer radius, the distance from x equals -1 to that outer part on my curve will be, in this case, 1 plus root y. That's because this distance is 1, and this distance is x, which is equal to root y. Rn will equal 1 plus y. So then the area of my slice will be pi times r out squared, which is 1 plus root y squared, minus pi times 1 plus y squared. And my volume will equal an integral from, now the y value is what you're looking at here. That lowest y is 0, the highest y is 1. They will not always be the same as the x value, so be careful about that. 0 to 1, pi times 1 plus root y squared minus y plus 1 squared dy. So now when we expand, factor out that pi, integral 0 to 1, we get 1 plus 2 root y plus y minus y squared plus 2y plus 1. And combine like terms, pi times the integral from 0 to 1, 2 root y minus y squared dy. Now the antiderivative of 2 root y is 2 times y to the 3/2 times 2/3 minus 1/2 y squared minus 1/3 y to the 3rd. Evaluated from 0 to 1. So that will give us pi times 4/3 minus 1/2 minus 1/3 minus plugging in 0 yields 0, which will equal pi over 2.